Great. So one more talk for the conference. It's our second budding talk, and like Carol will be talking to the Lowell Observatory. Will be giving us a review on magnetic fields of brown dwarfs.
Hey, can everyone hear me all right? All right, great. My very first science talk was actually at Cool Stars in 2014 in, where was that? I think that was Flagstaff. And I remember standing up there and telling people that we thought we were seeing radio aurora on brown dwarfs and the reception that received. So it's really fun now to see so many people get excited about this particular topic. Okay, let's see, hold on. Okay, the organizers of the Splinter session asked me to talk about methods for inferring magnetic fields on brown dwarfs and exoplanets. And so I thought it would be helpful to start with our own solar system, just to give us some context. Now, of the magnetized planets in our solar system, their surface radial average magnetic fields span 3 orders of magnitude. And some of them are dominated by dipoles, some are not. And then some dipole moments are slightly misaligned with spin axes. Saturn is almost nearly aligned, and then Uranus and Neptune are almost sideways, right? So, this is the diversity of magnetic fields in just our own solar system. And I would argue that at this point in time, we don't really even know what a typical magnetic field looks like for a planet, much less a terrestrial planet or even a gas giant planet. And if this is what we see in our own solar system, then just imagine the incredible amount of magnetic diversity that there might be at the very low mass end of the mass regime from brown dwarfs all the way through planets. And I would argue that accounting for magnetic diversity is really important for being able to characterize these systems because magnetic fields influence so many processes occurring in these systems. For instance, some of you will know that magnetic fields probably impact the composition of atmospheres and how they evolve over time, as well as atmospheric escape rates. We also think that magnetic fields may help gas giant planets lose their angular momentum as they're spinning down so that they don't reach breakup velocity as they would otherwise be expected to. We also think that magnetic torques may be very important for migration. Antoine, if you want to give me an easier figure, then I would be happy to include it in the talk. The time scale for magnetic torques impacting migration can be of order similar to tidal torques. And then finally, because magnetic fields are generated in the deep interiors where conductive fluid flows are occurring, they can also tell us about the dynamics of the interiors of these planets. Magnetic fields could even potentially tell us about the properties of satellites like moons, and I'll come back to this topic later. So hopefully in just that, single 1 to 2 minute grand tour of some but not all of the effects of magnetism in exoplanet systems, you all are coming away with a sense of the importance and centrality of magnetic fields and the role that they play in exoplanet systems. Now, measuring magnetic fields of planets in our own solar system is relatively straightforward if you have a funding agency like NASA and many, many, many engineers. So we can send instruments, we can send magnetometers on a flyby spacecraft like Juno. But measuring exoplanet magnetic fields is much tougher. And Mary Knapp, who is one of the Splinter organizers, is leading a team at MIT Haystack Observatory, designing what we hope will be the first or future large reconfigurable radio array that will be able to measure the magnetic field strengths of terrestrial planets. But until we master spaceflight, interstellar spaceflight, or we have something like go low. Right now, from the Earth, from ground, I would say that we can turn to what I've roughly divided into 4 broad categories of different measurement techniques, some of which give us indirect measurements and some of which give us direct measurements. Now, early on, around 2011 through 2015-ish, there was some interest in measuring pre-transit bow shocks, where essentially the idea is that you have this ionized material from the host star, that's piling up against the magnetosphere of a close-in planet, and then it gets shocked, and that dense material will absorb some of the starlight. And if you can figure out what the timing of that pre-transit bow shock is with respect to the actual transit of the planet, then that can give you a measure of the strength of the magnetic field. And you can kind of imagine that if it precedes the actual transit by more time, then the magnetosphere is bigger, and so that magnetic field is stronger. In the end, there were some challenges with this method. It was pretty degenerate with a couple of other methods or a couple of other processes going on in these systems, but most importantly, the stellar wind material is so hot, it's so ionized that you actually can't achieve enough optical depth to observe this. So this is probably from some other physical mechanism going on. Instead, we can turn to atmospheres and begin to potentially infer magnetic field strengths. Haley Beltz has been doing some really nice work over the last couple of years, where she's showing that the phase curves of hot Jupiters can correlate with their magnetic field strengths. And you can kind of imagine that ionized gases or winds on these planets are more likely to flow along a strong magnetic field. And if you have a planet that's weakly magnetized, then you might get more day side to night side wind. And so as a planet is going around a star, then if it's strongly magnetized, you'll see the peak in its phase curve very closely align with when it's facing you for a strongly magnetized planet. And if it's more weakly magnetized, then you get more wind flow. So that peak in the phase curve can offset from the center by a little bit. An independent test of her methods might come from Ethan Schreier, who has been looking at the magnetic, how helium-1083 nanometer absorption can trace magnetic fields, and in particular, the redshifts in this line. And so again, you can imagine if you have a strongly magnetized planet, then that magnetic field might contain some of the outflow, the ionized outflow from this, from a hot Jupiter. And so you'll get less redshift. And then if it's weakly magnetized, as is the case for the blue, then you would get more redshift. So all of these so far are indirect methods, but I think one of the most promising methods that is out there, and a lot of teams are working on this, is trying to actually directly measure the circular polarization and the magnetic broadening in the helium-1083 nanometer line. This particular method was pioneered theoretically by Antonio Eclipcic, who's now at Amsterdam. And you can basically see that as you get a stronger field, then the strength of the signal in both the fractional circular polarization and in the broadening of the line increases. And this method generated a lot of excitement when she first announced it at Extreme Solar Systems in 2018, partly because it looked like hot Jupiters might be very promising targets. So this is a dynamo model, a very famous dynamo model that unified planetary dynamos with a low mass star, late M dwarf and T Tauri star dynamos. And essentially it argued that for objects that are rotating quickly enough, the amount of energy, thermal energy that's getting convected in the interiors is ultimately the main ingredient that sets how strong the magnetic field of that particular object is. So the gray region is 3 sigma uncertainties on that. And basically they're taking this from a suite of thousands of numerical planetary simulations that they've scaled on up to these stellar parameters. So for hot Jupiters, where they're hotter because they have extra thermal energy from host stars, a very natural extension of this theory that Rakesh Yadav and Daniel Thorngren published in 2017 is essentially that if that extra energy from their host stars is deposited deep in their interiors, then you could perhaps produce several order of magnitude stronger magnetic fields, or order of magnitude stronger magnetic fields. And so if that was the case, then that would make searching for the helium-1083 nanometer line in its circular polarization and magnetic broadening a really exciting prospect because it would be order of magnitude easier to see this signal. I think we can certainly expect an uptick in papers searching for this signal in the next couple of years using instruments like Spiru, but the jury is still out as to whether or not current instruments are sensitive enough to observe this particular signal. Now, instead, what we can turn to right now are star-planet interactions, as several people have already touched on today. So when you have star-planet interactions can occur on both the host star itself and also on the companion or the planet. And essentially, Evgenia Shkolnik pioneered a method in the early 2000s where she was finding that she could see orbitally modulated calcium 2K emission in hot Jupiter systems. And the idea is that essentially, if you have a planet that's magnetically interacting with its host star, the picture here that she and Lanza developed is that planet is magnetically connected via a flux tube to its host star. And as it's orbiting the host star, it will drag the magnetic field around, and that will introduce friction at the footprints of that magnetic field, and that will heat up the atmosphere and cause this extra activity that you see. And from that, the power then allows us to indirectly infer the strength of that magnetic field. Using measurements of this particular signal, she and Wilson Cawley were able to show that you could plausibly get the strong magnetic fields that were predicted by the Yadav and Thorngren extension of the Christensen et al. Dynamo theory. But what I want to point out to you is that this squiggle here contains an efficiency factor that as of yet is observationally unconstrained. And so what they did in this paper was they actually tuned it so they could turn it up or they could turn it down until these magnetic field measurements aligned with predictions from the model. And this is the main point that they were trying to make was not to necessarily believe the strong fields coming from these systems, but it was just to show that for an efficiency factor that's somewhere between 0 and 1, they could reproduce predictions from this particular model. So it is plausible, but the measurements that they inferred do need to be independently verified. And so we can turn to, instead of optical star-planet interactions, we can turn to radio star-planet interactions, which in this case have the benefit of occurring at frequencies that give us very precise measurements of the magnetic field strength where the radio emission is coming from. And that means that closer in to the object emitting that radio emission, where the magnetic field is stronger, you will see a radio emission at higher frequencies. And further out where the magnetic field is weaker, you will see radio emission at lower frequencies. Now, in addition to the frequency, the flux density or the power of these emissions also matter. And they depend on properties from the stellar wind and also the magnetic field size or the size of the obstacle. Now, this obstacle size folds in information about planetary magnetic fields, because you can imagine that a magnetized planet may appear bigger because of its magnetopause or its magnetosphere than an unmagnetized planet, which will not artificially look bigger than its actual radius. And so these two ingredients actually make hot Jupiters potentially very interesting targets. So in our own solar system, essentially one of the pictures that we have going on is that we have a magnetized flow, in this case, the stellar wind or the solar wind. And if you have a conductive obstacle that's interacting with that magnetized flow, then that some of the power in that flow will get dissipated. And then some percentage of it will end up as radio emissions. And we end up with this really lovely scaling relationship called the radiometric Bode's law that all of the magnetized solar system objects align with. And so if we were to extrapolate that scaling relationship out to hot Jupiters, which are closer into their star, so they're seeing more flow and potentially have stronger magnetic fields, because remember the Yadav and Thorngren model, where maybe some of that extra heat from their host stars is going into inflating their magnetic field strengths, then you could potentially see radio star planet interaction powers that are several orders of magnitude stronger than what we see in Jupiter. And so if we were able to detect such aurorae from these hot Jupiter systems, that would be an independent means of verifying these magnetic field strengths that Wilson-Cawley et al. Inferred. Now, despite the promise of that, and many searches for exoplanet radio emissions, so far there have been no confirmed detections. There was a fair amount of excitement from Jake Turner's work back in 2021. But I think as of right now, last time I talked to him, nothing promising has come out of his follow-up observations. Now, what we do have instead are brown dwarfs. Did you say I have 3 minutes left for the? Okay. Did I have 20 minutes or 25 minutes? Yes. Okay. Yeah. Okay. I timed this. Okay. All right. So I may go over a little bit. So we do have brown dwarfs. Brown dwarfs bridge the gap from stars all the way down to gas giant planets. You can think of them as exoplanet magnetic analogs, just as they are similar to being exoplanet atmosphere analogs. Brown dwarfs also have the highest potential to power aurorae, just because they have very strong magnetic fields. They also rotate quite rapidly on the order of several hours, and they have largely invariant radii. Now, and that makes brown dwarfs really excellent laboratories for studying exoplanet-like magnetism. And when we place measurements of brown dwarf radio aurorae within the context of predictions for exoplanet dynamo models, we actually see a really interesting twist. So these brown dwarfs are isolated. They do not have a host star that can give them extra thermal energy. And yet, when we measure their magnetic field strengths using their radio aurorae, we find that they are stronger by several times than we would expect. And then in one of the more interesting recent developments in this particular field, in the last couple of years, Harish Vedantham's group at Astron have announced 2 144 megahertz detections of very cold brown dwarfs. They are following up these detections with higher frequency radio observations, but as of right now, If as of right now, there is the potential, depending on what they see, that these may constitute another branch of magnetic field strengths in the dynamo solutions for brown dwarfs. So we may potentially have strong magnetic fields, weakly magnetized objects to be determined. Now there is a very interesting twist here. And it's that this particular model is actually only valid for objects that have magnetic fields that are dominated by dipoles. And so this leads me to the last part of my talk, which is, we need a natural next question is considering what shapes are these objects' magnetic fields. So far, I've focused a fair amount on aurora. Radio aurora look like these strongly polarized, periodic, really bright radio emissions. But brown dwarfs actually have a second component of radio emission that's a little bit more quiescent. It's not as strongly circularly polarized. And so there was a small group of us for quite a while that we thought perhaps they might be radiation belts, as Jupiter also has radiation belts. So Jupiter has all of the magnetized planets in our solar system have these regions of extremely high energy electrons and protons that are captured in their large scale magnetic field. They're the most energetic structures in our solar system except for the sun. And we thought that perhaps brown dwarfs might as well. And if we could spatially resolve them, they could tell us something about the structures of these objects' magnetic fields. So to make this observation, you need to have extremely high resolution. In this case, at 8.5 gigahertz, you need a dish that spans the northern hemisphere of Earth. And so we put together 4 radio observatories for 39 total dishes. And over the course of a year, we were able to obtain 3 epochs that could resolve this really beautiful lobed structure. We also imaged the aurora as a sanity check, and as expected, it falls in the middle of these 2 lobes. And then around the same time, I was very pleased to see that Juan Bautista Clement published extremely complementary 4.5 gigahertz radio observations of the same system that confirmed what we saw. He will be speaking at 11:30 a.m. on Thursday in the plenary session. Please all go to his talk. He'll dig more into the physics. But essentially together, what we think we're seeing is the first example of a radiation belt outside of the solar system. Not only that, but it seems like 30% of brown dwarfs, at least, may have radiation belts. And in addition, binarity seems to enhance the occurrence rate of radiation belts in these low mass objects. That tells us, all these objects have radiation belt emissions. So that tells us that not only is convected energy flux not enough to explain their strong magnetic fields, but also their magnetic topologies cannot explain it. I swear I'm almost done. You may have noticed that I haven't really yet touched on these terrestrial planets. And this kind of brings me to the very close of my talk, which is that Io is responsible for 98% of the plasma in Jupiter's magnetosphere. It has over 400 active volcanoes, and Io, in addition, can excite aurorae on the surface of Jupiter in the Io-Jupiter interaction. So with the next generation VLA, we will be able to observe really detailed dynamic spectra. So that's time versus frequency versus flux of extrasolar aurorae. And if any of these systems actually have radio aurora that are being induced by satellites, then they'll produce these very characteristic arcs, and detailed modeling of that will be able to tell us about the properties of the companions, so about their spins, their magnetic fields, their ionospheres. Rob Kavanagh is working on inverting magnetic field topologies from systems that both could potentially have companions or maybe do not have companions. Please go to his talk on Thursday at 3. And in the meantime, while he's working on that, many other teams are trying to find examples of star-planet interactions from systems with known planets. I think that the best candidate so far would be the YZ SETI system that Sebastian Pineda and Jackie Villotson published just last year, and where they're showing some tantalizing evidence of perhaps orbitally phase-aligned radio flares. I won't say anything more than that, other than that Sebastian has a very exciting plenary talk on Thursday, so please go. And Jackie also has a poster up, so please see her poster. But the day that we are able to confirm that there are star-planet interactions occurring in a system is the day that we will be able to use those measurements to then characterize the low end of this dynamo model. And so using brown dwarfs and exoplanets, we'll be able to really fill in this particular dynamo model. So that was a big grand tour. I do have a review chapter that is now published. So if you miss any of it, there's a lot more detail in that chapter. Thank you so much. I did find
So we'll take one quick question. We'll find some time for discussion later, and I'll make sure we get to the coffee break. So
if you have a 100 gals subgroup there, a few days only, did you have a minister that captures between the third a quarter or the third of the whole? Would we see another signature?
Hot Jupiters are a really special, interesting case. So what I did not have time to get into here is that you do need to have a fairly low amount of low density plasma. If the plasma is too dense, then the radio emissions from the aurora can't actually propagate out. So there is some modeling out there from 2018. Daly Yates did some nice modeling that like suggested that perhaps hot Jupiters may actually have magnetospheres that are so filled with plasma that they can't actually, the radio emissions can't propagate from them. So one solution that they suggested perhaps was looking at supermassive Jupiters, hot Jupiters, which have a higher gravitational potential to help mitigate that particular effect. So yeah, it's much more, it's very complicated.
it's like Melodie.